Next up on our probability journey is the interpretation of variables, furthermore, as random variables. We already have the interpretation of variables being quantitative, categorical, explanatory, response. Here's another layer. We can also consider them as random variables. What we mean by that is that the outcome or the value of a variable depends on chance. Therefore, there can be probabilities associated with the possible values of the random variable. Let's touch base a little bit with some notation. Usually, a random variable is represented with a capital letter. Probably the most common are the capital letter Y, because Y makes sense as a response variable, or maybe X. And in defining a variable, this is a description of what is being measured or counted. So you might say Y or X is the height of a tree. So capitalization there. However, observations from that variable are usually represented with lowercase letters. So I might say lowercase y equals 6.1 meters. It's a minor distinction, lowercase, uppercase, but it does make shorthand notation a little easier. We're going to today discuss discrete random variables today, but this can also be expanded to continuous random variables, which is going to be most of the focus in our course, so I'm just going to say later there. Let's pop into an example to illustrate random variables and some properties therein, especially for discrete random variables. In this example, we're going back to coins, and let's consider a fair or unbiased coin being flipped 3 times. I'm going to let a letter represent the number of times a tail was flipped, and I'll use Y to be consistent and sort of general. So the capital letter Y here, it's a brief sentence describing what your variable is, what is being counted. Let's consider the possible values of this variable, lowercase y. If a coin is being flipped 3 times, it is possible to get 0 tails. It is also possible to get 1 tail, or 2 tails, and lastly 3 tails. And I want to dive a little bit more into these possible values because I think it's kind of fun to think about. We could draw a probability tree, however, I'm going to spare us the time in doing so. We did that in a previous video. I'm going to give myself a little more space here. Let's consider what 0 tails would look like. Well, wouldn't that be heads, heads, heads? For sure. Let's see what 1 tail could look like. 1 tail in 3 flips. You could have the tail in the first flip. You could have the tail in the second flip. Or that 1 tail could occur in the third flip. So notice there are 3 ways to obtain 1 tail. Let's go to 2 tails. two tails, that can be heads, tails, tails. I'm basically going to do the flip of what we got here. Two tails, which is one head. That one head could be on the first flip, on the second, or on the third. So we've got HTT, THT. That is what we call a heads sandwich on tails bread. And then TTH. So notice, again, there are three ways for two tails to occur. However, there is only one way to achieve three tails, T, T, T. I have hopefully hinted at what is considered a combination, right? There are three ways to get one tail, and there's also three ways here. Where did that come from? Consider 3, choose 2. 3, choose 1. And there's only one way for 3 tails out of a group of 3. Similarly over here, 3, choose 0. So hopefully that kind of connects the concept of combinations into some of this business here. I think it's kind of fun. Backtrack a little bit. Notice there are 3, 6, 7, 8. There's really 8 possible outcomes when you flip a coin 3 times. Let's discuss the probability of those 8 outcomes. We can discuss the probability that capital Y equals 0, the probability that capital Y equals 1, probability that capital Y equals 2, and 3. Let's take it from this top one here. Since we are dealing with a fair coin, each of these 8 outcomes all have the same chance. One of those 8 outcomes resulted in 0 tails, so that is 1 out of 8. 1 tail, there was 3 out of the 8. 2 tails, also 3 out of 8. And 3 tails, 1/8. What we have just defined here is called a probability distribution. It shows the random variable, its possible values such as 0, 1, 2, 3, and its corresponding probabilities. We're counting number of tails, right? Discrete, whole numbers. And here we've kind of got like a just a list of probabilities. We could even draw this in a type of graph. I've copied a set of axes here and basically going to transcribe these probabilities onto the vertical axis. So I'll label that probability. And our horizontal axis, I can just use the letter capital Y since I have defined it. But if you want to be more specific, you could also just not be as lazy as me and just write number of tails. And I'll put some tick marks here for 0, 1, 2, 3 tails. And I know I didn't put the 0 on the origin here. I just want it to be visible, so I've just offset it. Not a big deal. Our probabilities, going to need a tick mark for 1/8 and 3/8. I'll scale those, so 1/8, 2/8. I won't use you, I know you're a quarter. 3/8. In the past, we drew bars here, but there's another way that we can draw this, and is because these are discrete values, they're not ranging from -1/2 to +1/2. They're discrete. So sometimes you'll just put a line on those discrete values. So I'm putting a vertical line that's extending up to 3/8 there. 3/8 for 2 tails, and 1/8 for 3 tails. So these are both examples of probability distributions. Over here in the top, it's a list of the probabilities in written form. Down here, we've got a little graph. Everyone loves a graph. We can even discuss the shape of these probabilities over the number of tails, the shape of this probability distribution. It looks symmetric, right? You might even call that bell-shaped. And do you recall where the mean of a bell-shaped symmetric distribution occurs? Right in the center, yeah? So if we were to determine an average number of tails, wouldn't it be right here at 1.5? Definitely. And how would we compute that? Let's see. That's next. We're going to talk about the expected value, aka the mean of a discrete random variable. The way that this is formulated, we'll call this the mean. And because it applies to a random variable, often they'll put that letter for the random variable down there. So mu capital Y. And this is still a mean, so there needs to be addition and there needs to be division. And what would need to be added are the values for the number of tails. Add the number of tails values. So those would be the 0s, the 1s, the 2s, the 3s. However, those values occur at different rates or probabilities. So we would multiply by the probability of observing those y values. So all this text here is just to say those 1/8 and those 3/8. And we might as well just crunch this right on out for this example. Let's roll. The mean of our random variable, there's going to be a bunch of addition, only four quantities added. We'll start with the 0 tails, and that's going to multiply the probability for 0 tails, which is 1/8. That's going to simplify down to a 0, but I want to write it for thoroughness sake. We're going to add 1 tail times its probability of 3/8. Add it up. 2 tails, you also have a 3/8 probability. Last, not least, 3 tails, probability 1/8. And you certainly could just go and crunch away on your calculator on this, but I'm going to resist the temptation and notice that I've got a common denominator here of an 8. So I can do a lot of work without relying on a calculator. Here, remember that this is like 2 over 1, numerator times numerator, denominator times denominator, 6/8, and another 3/8. So this gives us a total of how many eighths? Looks like 12 eighths. Do you see it? 12 eighths is another way of saying 1 1/2. So we did it. Our hard work corresponded with our intuition up here. So this would be the expected number of tails in 3 coin flips. So if you were to flip a coin 3 times, and then 3 times again, and 3 times again, and every single time that you flipped a coin 3 times, we know that you might get 0 or 1 or 2 or 3, but on average, they should average to 1 1/2 tails. Something that I think is kind of fun here, let's keep track of this 12 over 8. 12 over 8. I'm going to scroll up. 12 over 8. Let's remember up here we had those 8 possible outcomes. And could you count up how many letter T's you see here? I'm counting them up. Isn't that 12 tails out of the 8 outcomes? It's kind of fun, huh? Okay. The mean's best friend is standard deviation. Standard deviation and mean are such good friends. Maybe this is what they look like. This is mu, and this is standard deviation. And they like to hold hands. Yay, they're best friends. Okay, enough of that silliness. Let's talk about the standard deviation of a discrete random variable. It still has the interpretation of being typical distance from the mean. But now we've got this new perspective with probabilities. We add up, take our observations, subtract the mean, standard deviation. We square those deviations. That's the sum of squares. And just like earlier, we know that those values occur with different probability, so we need to multiply by the probability of observing those observations. And you might remember a very classic feature of standard deviation. Our last step is always to square root that entire quantity. Let's illustrate this with our coin flip example. I'm going to need some space. Example. Okay, I will write that big square root. I think that will be sufficient. We're going to need to do some additions. But we'll start with 0 tails. We'll subtract the mean. Square times the probability of 0 tails. Cool. That's what they're all going to look like. We're going to have a subtraction squared multiplied by a probability. We'll have a subtraction squared multiplied by a probability. Okay, 0 heads, got it. 1 head minus the mean squared the probability of one tail, I apologize, it's 3/8. 2 tails, subtract the mean, your probability was 3/8. And lastly, we had 3 tails, subtract the mean, square your probability was 1/8. I would like to have more fun without any calculators present. No calculators allowed for the next couple minutes. I know that 1/2 is the same as 3/2. And you might be asking, why on earth would I think about a fraction? Isn't decimals easier? Not really, especially when you start squaring. For instance, what is 1/2 squared? Do you know off the top of your head? Probably not. I don't. But I know what 3/2 squared is. That is 9/4. It's pretty nice. So that makes our work a little easier, is considering some of these values in terms of fractions. Another value that we're going to see a lot is 1/2, and that will also be squared. We know that's 1/4. Okay, so I had some side action here. Let's get back to the task at hand. Here I see a negative 1/2 squared. I know that those negatives will cancel out when they're squared. So 1/2 squared, that would be 9/4. And I'll just keep that multiplication by 1/8 for right now. Let's see here, 1 minus 1/2. That's negative 1/2. But that needs to be squared, so that would be 1/4. These will all be positive because of that squaring feature, but now we won't have to deal with any negatives. This will be 1/2 squared, which is 1/4, multiplied by 3/8. And lastly, 1/2 squared times 1/8. Another cool thing we've got going here is a common denominator. You might notice that the denominator for all of these is 32. And so we can add up, we'll multiply and add up all of these numerators. Thank goodness these all have multiplications by 1. So we've got 9 plus 3 plus 3 plus 9. That's 24 in the numerator. 24 32nds. Another way to think about that in reduced terms is 3/4. Something that's kind of cool here, for those of you who've taken trig or geometry recently, isn't that root 3/2, which is a very popular quantity in trigonometry, and there we go. That is our solution. I would like to ask just a couple more questions regarding this coin flip example. I'm going to scroll down here. I would like to reinforce some of this notation, the probability notation, and I copy and pasted the probability distribution here with the coin flip example. And so I'm going to ask a couple questions. For instance, let's find the probability of flipping 2 or more heads. All right, and we're going to use the notation for this. Finding the solution may not be too difficult by utilizing these values over here, but again, if we were going to translate this question into the notation, I might say the probability that y is greater than or equal to 2. And I just realized this is not heads, this is tails, but I believe you understand what I'm trying to get at here. 2 or more tails. So I would have to use the symbol greater than or equal to 2. And this is going to require the probability for 2 heads plus the probability for 3 heads. Because 2 or more heads, remember the addition rule, 2 or 3 heads. So that's 4/8, also known as 1/2. Let's do that again. This time I'm going to ask the question, but not with words, but with notation only. Let's find the probability that our variable is greater than 2. So the distinct difference here is the exclusion of the equal to part on this symbol. So this is just greater than 2. Greater than 2 in a discrete variable, this is going to refer to only 3 tails. So our solution is 1/8. Let's do one more. Let's find the probability of at least 1 tails. At least 1 tails. With at least type questions, here we usually are asking for most of these probabilities. So sort of the longer way to do this would be to get, okay, at least 1, so the probability for 1 tails plus the probability for 2 tails plus the probability for 3 tails. Absolutely. And you'll notice that this is 7/8. That is correct. But often a quicker way to compute this is to instead realize that we want all of these probabilities, all of them except the top probability, which corresponds to 0 tails. So we could have written this is equal to all the probabilities except the probability for 0 tails, which would have been 1 minus 1/8, and that is the same solution. Alright, that's going to conclude this video. I'll see you in the next one about another type of discrete random variable called a binomial variable. See you there.